So let's start today's session. Just a second. Okay, so before starting this, okay, so you can hear me properly, right?
Yes.
So before starting the session, so I think it will be better if you introduce yourself and from which teams you join, because then it will be easier for me to navigate the contents later on. So can you please tell me from which team or I mean yeah, you are in one by one?
So I can start.
Yeah, sure.
Hi, my name is Prasoon, and I'm a PhD student, and I'm from Uttarakhand. Um, so I'm doing theoretical condensed matter physics, and yeah, that's essentially it.
What about others?
So actually, I'm Padmaja. I'm just doing B.Ed, and in SwayamPap, they asked me to just do a course, and I just selected this course. And basically, I'm not into physics previously. Just now, I have started it, but I find it very difficult to understand on all these concepts. So, what would be the things that is the basic things which I have to know and all these things, because everything lies to me for me like Greek and Latin. That's why.
Okay, so you're not from physics background, meaning you have not done physics graduation or something like any course, right?
No, like electronics and communication, that is before 20 years I did. And after that, now I have started with B.Ed and completely out
Mhm.
of line. But I want to learn about quantum physics. And so, what are the basics things? I thought from basics I can learn from here, but it is too high for my level. So, I just want to join this class.
Yeah. So I think the basic course again will be the quantum mechanics one course,
Oh,
and then condensed matter physics one course. So two basics courses are needed: quantum mechanics one and condensed matter physics one. And yeah, most of the contents will be covered within that region, but some few things might be beyond this. I mean, statistical physics and so on. But that those are very limited. I think the fractional quantum Hall effect will not discuss much.
okay.
So, so this is not supposed to be directly a uh, assignment solving sessions, but the problems are actually motivated from the assignments and similar problems. I mean, some problems may not be there in the assignments, but most of the cases it will be in line with the assignments. And you can pose also any doubts, and you can stop me anytime just to ask questions, either by unmuting yourself or in the chat box also. So preferably unmute yourself and ask questions.
just yeah, sorry to interrupt, but just to know, so you're also a PhD student or a
Yeah, we are
postdoc?
also PhD students. Yeah.
I see. Okay. So you're under Professor Basu or?
No, I am not under Professor Basu. I am from IIT Kanpur. So
Uh-huh.
we are
I see.
appointed
Okay.
from the PMRF scheme through which we have to teach in NPTEL or any other organization.
I see. And your research topic, if I can ask? Sorry for
Yes.
so many questions.
No, no, no. It's perfectly fine. In fact, it is better. My research topic is not perfectly the quantum Hall effect, but again theoretical condensed matter physics and quantum transport, uh,
I see.
related to quantum transport and quantum nature of the electrons and quantum and uh, things, but not precisely so much high magnetic field. I mean, I have few papers, but yeah, they are more focused now on low magnetic field regime, which is not the quantum Hall regime, which
I
is
see. Yes.
classical Hall regime, and sometimes quantum, and in all the cases, quantum effects dominates. That's my
Okay. Okay. Great. Thanks.
okay. So let's again start with the basics. I think Professor Basu have already did a very nice overview, but I'll just again go through this. Let me download it. So we'll be studying quantum Hall effects, not quantum Hall effect. Quantum Hall effect is one of the phenomena, one of the quantum phenomena that has been seen in the macroscopic experiments that you do with the nanostructures or the mesoscopic uh, uh, materials. Mesoscopics necessarily means few nanometers, of the order of few nanometer. Sorry for my bad handwriting. So few nanometer materials. So usually we have some few nanometer materials, and then we have high quality contacts or leads or electrodes, whatever we call it. We pass some current or voltage, let's say, and we measure sometimes the uh, hall voltage, or sometimes we also measure the longitudinal voltage. Okay, so this is the essence of our that's what experiment does. But depending on the situation and depending on the experiments, we can apply a magnetic field along the perpendicular direction, or sometimes just it is just the material that we choose, which will give rise to different phenomena. So these are typically four five mostly quantum Hall effects, let's say. So to begin with, this is the classical Hall. Just a second. Network connection is working. Okay, sorry for the interruption. I think some network issue. So you can hear me now, right? Hello, am I audible?
Yes. Yes, we can.
Yes. Okay, sorry. Okay, so any question, Padmaja? See hand raised.
No, sir, this is basic, so I'm just this. What is what only I'm just trying to just know it. That's what. So what else I can know? Please, detail me so that I will be knowing it.
Okay, so you mean how to start? I mean,
Yes, what? That's what I'm finding it difficult in order to just like correlate with all these concepts, because for each and everything I'm just trying to know what is definition, its formulas and all these things. I'm just finding it difficult. So how to just correlate with the topic and all, I find it difficult to understand.
Okay.
So as I have to submit the assignment and all these things, only if I know certain things and how all these things, like I find it difficult.
Mhm. So, okay, let me be very frank and honest. So, if you don't know the quantum mechanics basics, okay,
Mm.
uh, quantum mechanics basics one, the first one, and solid state physics basic, solid state physics one, then it will be a little bit above the bar. But quantum mechanics basics is a very general uh, thing, and it doesn't take much time to understand things of quantum mechanics basics and solid state physics basics. So these two things actually should be covered, not all the topics, but at least the idea of quantization. uh, so the idea of quantization, and then how do I write Hamiltonian, uh, etc. uh, these are the things for the quantum mechanics. And then solid state physics, the crystal structure, and then the crystal structure Hamiltonian, and then how do I how do electrons respond in an external electric field or magnetic field, especially the classical Drude theory. These things needs to be known actually. So there are a lot of topics in the solid state physics. In any classic textbook of solid state physics contains other topics, superconductivity and so on. But I think the key topics which in solid state physics needs to be done is that one is Drude theory. Drude theory. Second one is let's say uh, semi-classical motion of electrons. Okay, so this will be 3, and then in 2, the electrons in periodic solids. So electrons, basically the band theory of solids, electrons in periodic potential. So these three things are absolute must in solid state basics for this course. And in quantum mechanics, one, I probably cannot leave anything, because the starting from the quantization idea to Schrodinger equation and Dirac equation, in fact, in some part of it, is really necessary. So quantum mechanics one has to be covered almost everything. But solid state physics, these three things will do the work. We are going actually beyond the fourth thing. I mean, we are in the fourth thing. So the foundation is laid in these 3 points: Drude theory, electrons in periodic solids or periodic potentials, which is the electronic band theory of solids, and then semi-classical motion of electrons. I hope this helps. There are a lot of books, but there is one book by Simon, I think, from Oxford. That's a very thin book and very pedagogical language he uses to explain things. Very less details, but the content is very neat and clean. So this is one book, and there are multiple lecture note that can be there. But then it is better, I think, go by Simon. And then if you want more advanced books, then Ashcroft and Marmin. So this is advanced. So after Simon, I think it is better to read Evac and Luth. This is more easy to read language. So these are the things actually. And for quantum mechanics, there is the best books I think would be to Griffiths. Quantum mechanics by Griffiths. So yeah, I hope this helps. But yeah, so coming back to the family of quantum Hall effect. So this is first one is the classical Hall effect, where we apply current in some direction, let's say x direction, and then in z direction there is magnetic field, and we will measure the voltage transverse direction to the applied current, so which is the y direction, let's say here. And we find that there is a resistivity which linearly increases with the magnetic field, and which also helps to measure the electron density and so on. So those are explained by Professor Bosu. And then there is a quantum Hall effect, which again is the in the application of very high magnetic field. But instead of let's say, so this is my rho xy in classical Hall effect versus B, then it will increase like this, because rho xy is proportional to B for a classical Hall effect. And then but then for the quantum Hall effect it is not the case. If we find rho xy versus B, then initially it will increase as long as we are in the classical regime. Classical regime means here low magnetic field, uh, where the quantum phenomena still doesn't dominate in the response or in the system. And then we will see some plateaus in the resistivity. Okay, so these are kind of quantum jump of the resistivity. Instead of this linear increase, there is a quantum jump suddenly at certain magnetic fields. So this is the quantum Hall effect, and the course itself is devoted to understand how and why this happens, which kind of system we need to see this, and there are few associated phenomena uh, which have been discovered after we know of quantum Hall effects. So yeah, that's quantum Hall effect, and then there is something called anomalous Hall effect. This is called anomalous because in normal Hall effect that we are discussing, in even in classical Hall effect or quantum Hall effect, in both the cases we need external magnetic field to be applied. But then in some materials, in to be precise, in ferromagnetic materials, we just don't need any magnetic field. Although here they show the magnetic field, but in principle we do not need any magnetic field as long as there is a finite magnetization. In presence of finite magnetization in ferromagnetic materials, if we apply current in some direction, let's say x, and we measure the voltage in opposite perpendicular direction, y direction, then we will get some resistance and voltage. The term anomalous arises from this fact that we have not applied any magnetic field, but still there is uh, a Hall effect and a Hall resistivity. Here they applied magnetic field just to measure it. I mean, in experiments they always measure anomalous Hall effect by applying magnetic field also. That's a different thing. How do I differentiate classical Hall effect, anomalous Hall effect, and so on. But in principle the magnetic
Just one
field is
question.
not. Yeah, yes, sure.
Thanks. So when we have these ferromagnetic materials,
Mhm.
so there is a magnetization.
Right,
I'm wondering, for example, uh, in quantum Hall effect, I have my magnetic field as a parameter, which I
right,
can
right,
change from 0 to 10 Tesla. I don't know, but here I think it's the property of the material itself.
right.
So, I mean, is there a bar or some sort of a magnitude of magnetization which like which somehow governs that how equivalent it is to the quantum Hall system, or like, I hope I
Okay, so
explained.
yeah, sure. Uh, okay, so let me answer this, and if I don't clear, then please let me ask again. I mean, ask me question. So these
Sure.
are two different things: quantum Hall effect and anomalous Hall effect. And in principle, any ferromagnetic material, however small my magnetization should be or it is, I should be able to detect, or I should be able to show the anomalous Hall effect in the system. This is theoretical perspective, that it doesn't matter how much smaller magnetization do I have in the material, I should get anomalous Hall effect. But then in experiment we never get to theory precisely, right? There are a lot of things that comes into the picture when you do experiment. I cannot do selective experiment. When I do experiment, lot of other things come into the picture and then it gets detected. In theory, I can selectively calculate only one thing. I will only calculate anomalous Hall resistivity, right? I will not consider quantum Hall effect. I will not consider magnetic field. But in experiment, there are certain limitation and there are certain impurity and so on. So all of those things are combined and give me a combined signal. Now there are ways to detach the unwanted signals, but not always. So in principle, we should be able to have, we should be having anomalous Hall effect in any magnetized materials, however small the magnetization might be. But yeah, in experiments, it is better to have a strong magnetization. Then we'll get strong signal also. Remember, whenever we do experiments, there is noise in the signal. Any experiment you take, whatever precision, there will be some amount of noise. So the signal that we want should be greater than noise, right? So that's one limitation. But now there are a lot of sophisticated systems, or that the whole device is so sophisticated that even the smallest measurements we can also very precisely do by going to the cryogenic temperature, very low temperature, and with having a very clean sample and so on. That your question?
Yes, yes. Thanks for your explanation. But I what I understood was essentially that maybe we won't see the features of quantum Hall like edge states very cleanly in anomalous. It's just that they show some sort of that features, but for getting the like certain quantization as one see in the resistivity or conductivity plot, like one see in the quantum Hall, we need to have a strong magnetic field.
So for quantum Hall effect, strong magnetic field is definitely needed. Okay.
Yes. Mm-hmm.
But for anomalous Hall effect, in principle, we don't need any magnetic field. Okay.
Yeah,
In
yeah,
fact,
we don't need any magnetic field. Yeah,
right.
but my question was then that this magnetization, which is okay, arise from their like spin
They are intrinsic,
polarization.
right. They are intrinsic
Yeah.
magnetic moments in some
Yes.
magnetic material. All materials will
Hmm.
not show anomalous Hall effect. So is the quantum
Yes.
Hall effect.
Yes. Yes. So, but do we see edge states in anomalous quantum Hall systems?
Uh, so you are talking about this one, D, quantum anomalous Hall effect, or this one?
Yes. Yes, sir.
Yeah. So
Anomalous quantum Hall or quantum anomalous Hall effect. Yeah, which is the
yeah,
quantum version of
yeah,
quantum Hall.
quantum anomalous Hall effect actually arises due to the edge state. Okay.
Okay, I see.
So when I say anomalous Hall effect, it might be that so there is no magnetic field, okay, in anomalous Hall effect.
Mhm.
So let's say we are measuring rho xy, and then we are plotting it with respect to, let's say, number density or chemical potential. We can map number density and chemical potential with each other easily if I have the band
Mhm.
structure and so on. Then let's say I have anomalous Hall effect, something like this. Don't take this very seriously. I'm
Okay.
just drawing rough
Yes.
sketch.
Yes.
Now, if I in some materials, even in the anomalous Hall effect situation, I will have some kind of quantization. Let's say this is quantized. There will be a clear cut plateau, and then it decreases like so on. So when the anomalous Hall effect, in the anomalous Hall effect, we get this plateau like quantum Hall effect, then we call it quantum anomalous Hall effect. And this arises definitely due to the edge state actually. Let me tell you one more thing. I'm not sure it will be a bit advanced, but in this quantum anomalous Hall effect, the system is actually insulating. But what carries the current is that the edge state. So the bulk is
Yes.
insulating, meaning there is
Yes.
in the throughout the bulk there is no current, but along the edge there is edge state which are dissipationless. There is no
Hmm.
dissipation, and
Yes.
that
Okay.
edge state uh, I mean conducts electricity and give rise to this Hall effect or resistivity, whatever we talk about.
Mhm.
So if
I
we
see.
show a typical band structure, of any, I mean, again, this is a very rough sketch, so don't take it seriously. Then, so if I am here, let's say, if my chemical potential is somewhat here, and these are electronic bands, E versus K, then this is a insulating state, right? I mean, there is no density of states to conduct.
Yes.
There is no electrons here, let's say. Electrons are filled up to this energy and then you start from this energy again. So ideally, this is kind of insulator when I have chemical potential in this gap region. But in quantum anomalous Hall insulator or in quantum anomalous Hall material, there is kind of edge state that develops. So this is kind of a single state that goes through this bulk insulating state. So this state actually conducts electricity for this quantum anomalous Hall effect, which occurs in quantum anomalous Hall insulator. Insulator because there is a bulk band gap, but there is only one or two or three, maybe depending on the material, there is edge state that conducts. Okay,
Okay.
so that's
Thanks for your explanation.
uh,
Mhm.
quantum anomalous Hall effect. And then so whatever, so in this case, in this four cases, we are talking about electronic charge transport, right? But in the spin Hall effect, we actually talk about the electronic spin transport. Electron have intrinsic spin associated with them, so there is a spin transport. So what really happens is that in spin Hall effect material, I mean, this has to be strongly spin orbit coupled materials. In some materials, it's so that whenever I apply current in the, let's say, x direction, and again measure the voltage in y direction, I will get spin polarized current. So so let's say this is down spin. So down spins are goes along this direction and up spins goes along the opposite direction. So there is no net charge current, right? So no net charge current. Charge current is zero because some electrons are going in this direction and same amount of electron are going in this direction, right? So so the charge current actually cancels, but then spin up electrons accumulates in this edge, whereas spin down electrons accumulates in this edge. So there is kind of Hall effect of spins. So that's why we call it spin Hall effect. And then when this spin Hall effect again becomes quantized, kind of this type of again plot will be there. When it becomes quantized, then we call it quantum spin Hall effect. That probably give rise to the birth of topological insulators, and we can say topological material itself after this spin Hall effect and quantum spin Hall effect.
So, in one question, just
Yeah.
in quantum spin Hall effect,
Mhm.
what is the measure? Like we know that we're gonna measure the spin,
Mhm.
which gonna transfer from
Right,
one edge to other.
right.
Uh, but like we have conductivity, but what we plot essentially is
Yeah, yeah. We will again plot the conductivity or the resistivity, but then again remember that there is no current net current in the sorry net electronic charge transport in the system, right? So there are ways to detect spin polarization. So if you measure in this edge, let's say at the in this edge there is a accumulation of down spins, right?
yes,
And in this edge there is a accumulation of up spin. So there essentially there is a development of spin angular momentum in this edge, and at this or at the opposite edge the spin angular momentum due to spins will be exactly opposite. So there are many ways to detect this spin polarization and spin angular momentum. One particular useful way is that magneto-optical Kerr effect. So these are different things, but again the essence is that they apply some optical field, and if and depending on the spin angular momentum or the spin, the light polarization will be slightly rotated. So
hmm,
light polarization can be uh, again these are a little bit advanced, but light polarization can be randomly, the vibration can be random. So
yes.
this is unpolarized. and this is linearly polarized, let's say in one direction, in any particular direction, so linearly polarized, and then there can be circularly polarized, right?
Mm-hmm.
Depending on how the magnitude is, let's say this is the light's electric field, and then if I have E0 plus I E x y, this will be along y direction and this will be along x direction, and E0 x equal to E0 y, this will give rise to circularly polarized light, right? So then again, depending on how the system the device works, they can send linearly polarized light, let's say along x direction or y direction, and then due to the interaction between light and this spin angular momentum accumulated at this edge, there can be a rotation of the polarization of light, let's say by this angle theta, and for this end there will be a rotation at the opposite angle minus theta. So that's how we can also measure the spin polarization. I'm sure there are many other ways, but I'm not aware of all the experimental developments.
Yes, but just sorry to, but just last question.
Mhm.
I don't understand the fact that how the spin
Mm.
translates its information, like how one can, okay, we have spin Hall effect, but
Mm.
how, looking at the plot of resistivity or conductivity, I can infer that I have spin quantum Hall effect. Like,
Okay,
uh,
so that's a nice question actually. So one way is to, I mean, I can theoretically plot things, but then experimental way can be different. So
mhm.
theoretically, what I can do is that I can literally calculate the rho xy for, let's say, up spin, and then versus chemical potential or number density, which is more familiar to the experimentalist, number density. So then I can plot whatever it will look like, and then similarly we can also plot down spins. So this is for the theory people. I mean, we can literally do that.
Yes.
But for experiment, what they do, I am not really sure. But one way is definitely this uh, magneto-optical car effect. But in terms of resistivity, I'll have to look and say in the next class.
No problem. No problem. Okay. Thanks.
Yeah. So any other question from anyone else? Please feel free to ask questions. Actually. Okay. So this was sort of introduction what we'll cover in this series of sessions, or whatever Professor Basu will cover. Then there are other quite a few things like fractional quantum Hall effect that he will cover, and anomalous Hall effect, quantum anomalous Hall effect, and the counterparts for the spins will definitely be covered in detail. Spins, yeah, spins will also be covered. So any questions? Okay. So so basically in quantum Hall effect we have quantization of conductivity, right, or the quantization of energy itself, because in classically our system will have some energy in terms of, let's say, kx and ky. If I talk about two-dimensional system, then let's say I'm talking about 2D parabolic system or free electronic system. Then I will have energy, or let's say first write the Hamiltonian. This will also be the energy actually. So h square by 2m kx square plus ky square, right? So this is the free energy Hamiltonian for a two-dimensional electron gas, and then the energy will also be similar if you diagonalize kx square plus ky square. So these are continuous in k. If you plot this energy spectrum, uh, so let's say if you are plotting with kx and then energy, it will have a simple parabolic like structure like this, and similarly with kx or ky, the things will be same. So there is a continuous energy in this system, right? So as kx increases, the energy increases in a parabolic fashion. So this is the classical regime or the conventional regime where we get Hall effect, just the conventional Hall effect. We have a system and then apply current in, let's say, x direction, and then measure the voltage in y direction, right? Vy. This happens again, Professor Bosu explained, so I am not repeating things, but this happens due to the Lorentz. Okay, so there should be also a magnetic field which we assume along the uh, out of plane direction to this page, which is z direction. Okay, so magnetic field, and due to the magnetic field, the electrons will experience the Lorentz force uh, minus E v cross v, and then also due to uh, electric field, there will also be a force of electric field, and as this, let's say, so let's again draw. So this is x direction, so the electron will be flowing along this direction, so minus x direction. So V will be parallel to the minus x direction, and then there is a magnetic field in the z direction. So what this force will do is that this force will be along the minus and then minus x cross z cap, right? So essentially x cross z cap, which will be minus y. So the electrons will get deflected along the minus y direction. So this is x, y, and this is out of plane z. So if this is y, then in the minus y direction, so along this direction, the electrons will get accumulated. If electron gets accumulated, more and more electron gets accumulated in the minus y direction, then there will be an effective positive charge or positive voltage along this direction, and this actually at some point of time there will be a equilibrium situation where there are no more electrons that can flow to this direction because of this positive charge development, because the electrons are actually flowing along this direction, and due to the Lorentz force they are trying to come here, but then a net positive charge or positive atmosphere has been built up uh, in the positive y direction, so they will also feel attracted to this positive environment, right? So there is a competition going on, so the Lorentz force tries in this direction, uh, and then the positive environment tries to move in this direction, so there will be a net equilibrium situation after certain time. uh, then we'll have some voltage development along this y direction, so that voltage, sorry, Hall voltage will be proportional to B by Ne, where N is the electron density or hole density depending on the type of carrier. Sorry, Nq, it is better. So N is the carrier density actually, and Q is the charge. It can be electron or it can be hole. So that's the story of uh, classical Hall effect, and it's kind of all the things are classical. So we are treating everything starting from the Lorentz force, and the system itself is classical. I mean, the Hamiltonian itself is also classical. So, so that explains classical Hall effect. Now, when We talk about quantum Hall effect. As the name suggests, there is some quantization happening in the system, which is reflected by this resistivity versus uh, magnetic field plot, where these plateaus are quantized at some very particular values. It's not random at all. So this quantization is actually a manifestation of quantum mechanics at play in the system. Uh, and the first thing that we read or that we study in quantum mechanics is that quantization of energy. So the concept of quantized energy. Instead of this continuous curve, which we have shown in for the free electron parabolic system. In the quantized system, the energy levels are discrete. So there can be like this one, this. So there are no states between these two energy levels. So let's say this is E0, E1, E2. And the simplest example that we study in quantum mechanics is the any particle at a box, right? Let's say this is L, then energy becomes n square pi square by 2ml square. I think h square is also there. Yeah. So n can take 1, 2, 3, etc. So depending on the n, we can have some energy levels like this. There is no continuous energy level like free electron cases. So in quantum Hall effect also, there is a quantization of energy that happens in presence of magnetic field only. Okay. Uh, Again, this is a basic solid state physics, but uh, so whatever we talk about or we will talk about in this series of sessions is that we're essentially talking about solid state system or quantum physics, one part of the quantum condensed matter physics that is being actively studied. So let me tell you that electrons in a periodic system. So we will only talk about periodic system throughout the course, but sometimes we will confine our systems to, let's say, this is Ly and this is Lx. Okay. So nonetheless, we will assume that there is a periodicity in the periodic potential. So in solid state system, what really happens is that there are some ions, right? And then around that the electrons are there, uh, electronic orbitals are there, and they are periodically arranged. Means this distance, if it is a, then this distance is also a. If it is a two-dimensional system, then it is along the x direction, and same thing will be there in the y direction. And there are some potential, right? So due to the ionic potential will be there. So it's the potential will be like this somewhat. At the position of the ion, there will be a very negative potential, right? And then again, as you move from that particular ion, the potential will start decreasing. So this is, let's say, somehow zero line, and this along this direction, this is negative. And this again basically Coulomb potential that electron will experience. So Coulomb potential, so minus, so what really happens, q by 4 pi epsilon naught r, right? So these are periodically arranged, and in band theory of solids, what we read is that in the periodically arranged atomic system, we will have some energy spectrum. The electrons will be again quantized, not in the sense that we are going to study few minutes later, but the electrons will be there in the form of bands. Let's say, I mean. So what really happens is that, let's say, this is crystal momentum and this is energy. So let's say there is one band like this, and then there is another band like this, and then let's say another band like this. Okay, I'm just drawing very roughly, but what really it tells us that this is one energy range. So let's say this is the maximum point of E3, third band, and this is the minimum point of E3, E3 min. And similarly, we can assign this is as E2 max, and maybe this one as E2 min. Again, same thing, E1 max, or maybe this one, E1 min. Okay. So even in presence of a periodic solid or periodic ionic arrangement in the solid state system, so there is some kind of discreteness in the system's energy. It's not, so the energy bands are not like something like how do I draw? So let's say this one. So let's say this is zero energy, and this touches also the zero energy. It's not like that. Okay, key the electrons can be here, the electrons can be here, here, and here. It doesn't happen in most of the cases. In metallic system, of course, we have some band overlapping, but in general, the bands in the solid state system have sorry, electrons in the solid state system can only stay up to a certain energy level. So if it is in the first band, so then so that basically the energy levels forms bands. So this is one particular band. Within this energy range, there can be electrons, and then electron can occupy this particular energy range, which we call bandwidth. Okay, so this much is the bandwidth, and again similarly for this third band also. So so the idea of discreteness already comes into the picture when we talk about quantum condensed matter physics, or we take into account of the periodic potential of the system. Okay, so this is one kind of uh, so this is one kind of moving away from the purely classical system where we will have continuous energy increase in the parabolic system, but there are certain energy levels which are forbidden. So basically, if we think about this particular region, this shaded region, so this is forbidden region. Okay, there are no states where electrons can stay around this energy. So this is one kind of sort of first introduction to the quantization in terms of solid state physics. Of course, when we talk about quantum mechanics, then we start thinking from the photons perspective, and so on. Start from the Einstein's explanation of photoelectric effect and so on. But in solid state physics, this is kind of band theory takes into account that the fact that electrons are not in a very continuous energy spectrum, but there can be some forbidden region and there can be some allowed region. Within that allowed region only, the electron will have that energy. So again, this was the basics, but when we apply external magnetic field, there is a different kind of quantization that forms in the system. Now we will talk about those energy levels after applying the magnetic field. So these energy levels, which I roughly tried to give a sense, is that in presence of zero magnetic field. So a system is there, a periodic solid state system is there. Due to ionic potential of the system, there is some kind of formation of bands where there are some allowed energy regions and there are some forbidden energy regions for the electrons. Now what we will talk about is that Landau levels in presence of magnetic field. Okay. Again, these are nothing but energy levels. Let me write. So that will so this Landau levels will give us a very clear clue about what really happens when we apply magnetic field in the system, and how this quantization thing happens actually. Okay, so again we'll take the example of 2D free electron gas. That's the simplest example. So 2D sample lying in the xy plane. So this is, let's say, kx and ky, and we have applied external magnetic field along z direction. So B is parallel to z direction. Okay. Now we need to take into account of the effect for this magnetic field. So again, in the classical mechanics that we read, the effect of magnetic field in a system or a particle, we can actually go by this only. So we first write down the Lagrangian for the free electronic system or free particle. So okay, so it's kind of, you can actually map to this free electron picture to the free particle picture of classical mechanics. In classical mechanics, there is no concept of quantized energy levels, definitely. So I'll talk about where you stop at the classical level and where you start at the quantum level as you go along. So this is Lagrangian in presence of, let's say, magnetic field dot A. X dot is the velocity, and x denotes here the generalized coordinate, okay, which includes x, y, and z if necessary. Okay, x is a vector actually. So x generalized coordinate. So this is again the free particle picture, half mv square. That's the kinetic energy of the free particle, and this terms arises due to the magnetic field B, where B equal to curl of A, right? So due to this magnetic field, there is an extra term that comes in the Lagrangian. And from this Lagrangian, we find Hamiltonian, again, the same classical physics uh, that we read in basics course, P plus EA square. So this was the Lagrangian, and this is the Hamiltonian. So derivation of this can be found in any classical textbook, okay? I'm not deriving this, but essentially this is the Hamiltonian in presence of a magnetic field for a free electron gas. So we'll start from this equation actually. So there is a shift, or there is a correction to the momentum in presence of a magnetic field that happens for a system in magnetic field. Now to so basically we stop here in the classical mechanics course, that the Hamiltonian changes due to the electric field, and if there is an external so due to the magnetic field this one is, and if there is external electric field, then we will also add the phi, right? The potential, electric potential due to the electric field, but we are not accounting for the electric field, but we are only concerned about the magnetic field here. Okay, so this term will not be there. Okay, so our task is to, for when we are in the quantum regime, our task is to solve this Hamiltonian and find the energy eigenvalues of the system. So So what are the energy eigenvalues of the above Hamiltonian? Okay. Okay, so for that so as our Hamiltonian is of the form of 1 by 2m p plus ea square, these are vectors. We need the form of E, right? And what we know is that B is along the Z direction. So there can be different gauge for this choice of A, which can give rise to the same magnetic field. What you choose here is the Landau gauge. A is the x d y cap. So if you do curl of A, you see if you calculate just two line calculation, you will get B z cap. Okay. We can have some symmetric gauge also, where there will be x b and minus y b, similar some kind of thing, but again this is very easy to calculate with the Landau gauge. So this is Landau gauge. Any gauge you choose, as long as the magnetic field you get curl by doing curl of A is the same magnetic field, it's fine. So any question at this stage? Okay. So if we write explicitly, P plus EA will be what? So P means Px, let's say x cap plus Py y cap, and then plus E Ax x cap, x component of the vector potential, Ay y cap of the y component of the vector potential, and there is only y component, so we'll have Px x cap plus Py y cap plus Ay y cap. Okay. So essentially this becomes Hamiltonian. If you write, then it becomes 1 by 2m px square py plus so okay, so let me elaborate more. So again we are back to the p plus ea square, or let me write, you can write square as dot product of two vectors, and then px x cap plus py y cap plus ay uh, y cap. The same thing. Okay. So if you do this dot product simply, then you will get px square plus py plus eay square. This will be px square plus py plus ebx square, right? Because ay was xb. Okay. So from this thing, you note that the translational invariance of this Hamiltonian along the x direction is lost, right? Because there is explicitly x sitting here, but whereas there is no y uh, in this Hamiltonian. So translational invariance along the y direction is intact. So let me write. Intact. And again, just a side comment, how do we check translational invariance? So quantum mechanically, let's say I am checking translational invariant along x, right? So what we do is that we take commutator with respect to that momentum direction. If we get 0, then it is invariant. Okay, if it is not equal to 0, then not invariant. And it is easy to see why this will not be invariant, because in this particular Hamiltonian we have x, right? And we know px and x doesn't commute, it is rather minus I h bar, right? So the commutator of px h, which is px h minus h px, will not be same for our case. And why you are calling then the translational invariance is gone for x direction, because we know the momentum as the generator for translation. Again, it's a classical physics as well as quantum mechanics. So px being the moment generator of translation along the x direction, and px doesn't commute with the Hamiltonian, so the translational invariance along the x direction is lost, and translational invariant along the y direction is intact because there is no y, so py will commute with the Hamiltonian. Okay. Okay. So otherwise, if you see,
Just
yeah,
one small
yeah, sure.
question. The word intact means
It remains same, basically
okay.
translationally invariant.
Yeah, so it will be okay. Translationally invariant along y.
Right, right.
I see. Okay, thanks. Thanks.
Okay, so otherwise, so let's assume that we do not have this part. Okay, for a second, we do not have this part. Then what the Hamiltonian looks like? It's actually looks like again the free particle, and free particle wave function for a quantum mechanics becomes e to the power iky, right? Or ikx, depending on which direction I have that translation in bit. So if my Hamiltonian is simply 1 by 2m px square plus py square, then the wave function simply be around e to the power iky and e to the power ikx with some normalization factor. Okay, but here, although y can be there, psi in our case psi can be, psi is the wave function, so e to the power ik can be there, but there cannot be e to the power ikx, because this is wave function for the free electron case, which is translationally invariant along both x and y. This term cannot be there, rather there will be a function of uh, x which also depend on k is the crystal momentum. So this is the wave function that we have to choose. Again, I will not derive the full derivation. Full derivation can be found in many books along with the David Tong's lecture of quantum Hall effect. But so we have to choose this kind of wave function because of translational invariance in y direction, and it is not in the x direction. So what we get is that each Hamiltonian will be simply, so if you operate this h on psi and then find out what will be h. Okay, so these are the because so let me write better. So it will be 1 by 2m px square, and by the way, these px are all operator. Okay, we are not writing explicitly cap sign, but in quantum mechanics everything is almost operator. Hamiltonian is also operator, so any observable are represented by operators. So we are not, will not be writing throughout this sessions or all sessions, we are not writing this cap, but essentially they are operator. Px square plus py plus e by, let's say, square, sorry, ebx, and we are applying psi. So again, we are calculating up to a normalization factor. So let me call it just constant, some constant. Okay. constant normalization factor. So Cn and then e to the power I k y, and if some function of x, if we apply this, then the py will directly operate on this e to the power I q y and just simply give the momentum along the py direction. So it will be 1 by 2m px square and then h bar ky plus ebx square, and then similar thing e to the power I ky fkx. Okay. Again, some just calculation jugglery, we'll detach this px square and then we'll write it as m omega b square by 2x plus ky lb square and then whole square. Okay, where omega b is eb by m and lb is root over h bar by eb. So should I directly calculate this one or I can skip? Let me know. So if you feel I can actually calculate, no issue.
For me, it's good. I mean, you can skip. I don't know about others.
Okay, so what we have done is just the simplification. So sorry, px square by 2m, and then we'll take something out of this. So let's say we have to take h bar ky by eb plus x square, and then this will be like of e square b square. Okay. This will be the term, and there is wave function part is there obviously. So from this we will have px squared by 2m plus 1 by 2m, and then half e square b square by m square, and then m. What we have done is that we have written this m as m square and 1m in the up, and then x plus h bar ky by eb square. So this will be px square by 2m plus half. So we'll write this part as omega b square and then m extra and x plus ky lb square. Okay, lb has the length scale, so lb has a unit of length, so this will give me length, and this is also length, so dimensionally it is also consistent. Okay, so that's how we got this Hamiltonian, and this is a very familiar Hamiltonian, right? This is a Hamiltonian of harmonic oscillator. Except for the fact that there is an extra KYLB, but that's a that we can think of as a displacement of the zero position. So usually what we have Hamiltonian, or sorry, simple harmonic motion around the x equal to 0, let's say 1D simple harmonic motion, and then for some reason or for some effects of let's say external field, our maybe we can think of like the motion or the harmonic motion is happening like this. Okay, where the midpoint lies around this point instead of this point of this. Okay, that's how we can think. This Hamiltonian have detailed solution, and to get by solving this harmonic oscillator problem, this in itself can be a problem, that just find out the energy eigenvalues of harmonic oscillator. What we get is the quantized energy levels h bar omega n plus half. Okay. Okay, so in energy there is no effect of this KYLB because it's kind of just shifted harmonic oscillator. Okay, but that's essentially the same frequency is there, omega b. So this is the energy eigenvalues, and we have solution for the harmonic oscillator, wave function solution for the harmonic oscillator, which goes like x and y, which is like e to the power I k y, and then Hermitian potentials, sorry, polynomials, x plus ky lb squared and then e to the power minus x plus ky lb square by 2 lb square. So this is the solution for the wave functions again. But what is important is that it's so harmonic potential was one problem. In that case, what we had is that we had a particle in that potential oil box, right? But the potential was like m omega square x square, m omega square x square or y square, whatever, in which direction the motion is happening. So this was the problem of harmonic potential in the quantum mechanics. What we found out through this calculation is that free electron gas in presence of a magnetic field is also behaving like harmonic potential, and so is the energy. So the energy levels are independent of any k, where so let's say this is energy level, this is n, so then for n equal to 1, n equal to 2, and so on, and the band gap between the two, or the distance between the energy levels, are uniform. So En plus 1 minus En equal to h bar omega b. So there is a direct correspondence between the particle in a harmonic potential and then free electron gas in magnetic field. And this gives us the first clue about the problem of quantum Hall effect. Because quantum Hall effect experiment was also done in some MOSFET where the electrons behaves as free particle in absence of magnetic field. But when we apply magnetic field, then essentially what really happens is that this Landau level energies gets created, where so basically this is a transition from so this is v not equal to 0, and v equal to 0 we had again the same parabolic thing, kx or ky or ky. This will be like uniform, it should be. So there is a transition or the transformation from this point to this point. Okay, so there is a so from continuous energy spectrum there is discretization of energy. So as you can speculate that whenever my chemical potential or the for a system where the chemical potential lies along around this direction, sorry, this position, which is kind of in the forbidden region, there is no electronic states around this energy, so there will be no conduction that is happening. Okay, and then again if I increase the magnetic field, then it will be so okay, so let me tell you another interesting point also, that this energy, sorry, so this energy is proportional to h bar omega b, which is proportional to ev by m, right? So the energy levels are proportional to the magnetic field. So as you increase the magnetic field, the energy levels, so this was, let's say, for at some energy n equal to 1, b equal to b0, if we increase the magnetic field, then the new Landau level for the first energy, quantized energy level, will be at higher energy. energy is directly proportional to the magnetic field. So let's say this is B equal to B1 and B1 is greater than B0. So now if I fix the chemical potential, let's say here, my chemical potential is fixed here, and then I am increasing the magnetic field. So these levels should go up and up and up, right? And this actually creates a transition of states, because there are a lot of Landau levels like this. N can go from 1, 2, 3 and so on. So there are a lot of Landau levels. Let's say somewhere we have mu, and there are many Landau levels, quantized Landau levels. So this is mu line. So as you increase the magnetic field, one Landau level will go above the chemical potential, and as you keep increasing the magnetic field, this will keep happening. Now the interesting point is that the concept of Fermi function and occupation function in the solid state system says that, let's say I have it at 0 temperature or around 0 temperature, above Fermi energy there can be no electrons, right? So the Fermi function exactly looks at 0 temperature. It is actually a sharp step function. So this is Fermi function, and then this is energy or chemical potential, whatever you call it. So this point is chemical potential actually, this one, and this is energy. So if these energy levels go above this mu line, energy, then there are no states. Electron have to drop to the below mu states, because these states are occupied and there are no states above mu around 0 temperature. So this actually indicates that there will be some kind of transition that will happen as we keep increasing the magnetic field, because once a Landau level goes above the Fermi level, the electrons cannot be there, right? Because at 0 temperature there is no occupation according to Fermi function. So the electrons will be forced to jump to the below Landau levels, and this kind of gives rise to the uh, jump in the resistivity also. So we'll read these things, or we'll also explicitly derive these things in more detail, which we call Subnikov-Diaz oscillation. But essentially, this is one of the pedagogical way of understanding that there should be some kind of quantization in the response. Response meaning here resistivity or conductivity. Once I apply very strong magnetic field, so that there is a formation of Landau levels in the system. Okay. Okay, so I hope the points was clear, but let me know if you have any question up to this point.
Good evening, sir.
Yeah, yeah.
Sir, I want to know whether from the band structure, can we predict whether the material is topological or not?
Okay. Whether from the band structure.
Just by looking the band structure, is it possible to?
So what you are saying is that I just have a band structure, energy versus K, right?
Yes, sir. Yes,
Some like this.
yes,
I can say topological or not.
yes.
I would say you cannot. The reason is, even parabolic like band structures sometimes show topological behavior. So where we get parabolic or free electron type dispersion in some metals, right? In some metals we get that. In
Yes,
some semiconductors also we get that. There
yes,
is gap, but essentially the dispersion is the same. In order to be topological, first thing is that is there any topological invariant in the system? Whenever we say that the system is topological, some kind of index or some kind of quantity is there for that system, which will be non-zero. It's kind of you can think of like Landau theory of ferromagnetism, Ising ferromagnetism, where you say that magnetization is non-zero below Tc, magnetization is 0 above Tc, but then don't I mean directly correspond with these two. They are completely different. But all I'm trying to say is that you have to calculate some kind of topological index or topological quantity from that band structure. If it comes to non-zero, then only we say that that band structure is belongs to topological and the material is topological, material is in the topological state. Okay, so by reading the band structure of energy versus k, we cannot really say.
It means theoretically we have to derive some topological
Right,
parameters.
right. Theoretically, we have to derive some topological index. There are some parameters already in active study, like Chern number, Z2 topological index, and Valley Chern number, etc. These things I'll partially cover, not much. When we talk about anomalous Hall effect, its connection with the Berry curvature and how the Berry curvature actually give rise to the Chern number. And in some cases, even if the Chern number vanishes, it doesn't really mean that that material is not topological. So there can be multiple, many type of topological materials. Okay, in some cases, Chern number vanishes, but then there is something called Z2 topological index, which can be finite. So that's a different kind of topological index and different kind of topological material.
Thank you, sir.
So any more questions or yeah? Okay. So today is the first day. So let me stop here. But before that, let me ask from you guys that what do you expect from these sessions? I always ask this question to whenever I teach in NPTEL, so that I just have an idea of what I am doing and what the participants wants me to do and what NPTEL asks me to do. And there may not be sync in all three, but I try to do that if possible. Any insights or any inputs?
Sir, I have one question.
Hmm. Sure.
Can I ask the question now?
Sure. Anytime you can stop me and ask questions. These are supposed to be doubt clearing classes.
Okay. So it's like same question as previous asked. So yeah, if consider I have a novel material, like for example, exin material, any exin material. So now I need to find is it topology or not, or else any material, a random material which is topology or not. So what are the steps I should be following? Like I can do computationally also, but like how? Like what is the process? Like what is the steps we want to follow so that I can able to say it's a topological material?
You want to answer from a theoretical perspective, right?
Theoretical, yeah, theoretical, and it should also implement a practical also,
No,
like from
practical
experiments.
implementation is always there, but it is always bit tricky than theory. As I was keep saying in the first half or in the towards the first of this session, that experiment detects everything, right? I mean, in theory, I can say ki I'll switch off magnetic field and do calculation. I'll not take this kind of thing and I'll do this kind of thing. I'll take this approximation. All of these things are like in our hands. I'll not do this, right? Of course, there has to be some consistency and there has to be check and balance that what start system I am studying and what approximation I am taking, there should be in coherence as much as possible. But in experiments, there are sophisticated experiments which can detect that the system is in Chern insulator phase, or the system is in Z2 topological phase, or some Valley Chern phase. There are different experiments that can tell you. So let me tell you the first the experimental thing, and then I'll come to uh, theoretical side of this. But I think let me be fair to say that I myself do not understand topology very perfectly, in a sense that it is a very abstract mathematics concept. In physics, we understand things very in a very lucrative manner and very easy way to understand, but there are a lot of things. So yeah,
Okay.
so there are different topological indexes or topological phases, let's say. One is Chern insulator, and second one is again I can say Halley-Chern phase, and then Z2. Uh, okay, so you guys know concept of Berry curvature.
Yeah. Yes. Yes.
Okay, so if others don't know, then it will be difficult. But there is something called Berry curvature, which is a property of electronic wave function. Okay. So in all of those things, we are mostly concerned about the electronic energies, right? In the classical textbook of Ashcroft Mermin, or let's say even during the quantum Hall effect, we will not talk much about the electronic wave function. Later on, we will connect these two things with Chern number and so on. Then we will also talk. And then only we will talk. But this is so for now. Let's assume this is a property of electronic wave function, and Berry curvature, which we denote by, let's say, omega, and I'm talking about Z component of the omega. It's kind of curl. That curl is in the momentum space, and uh, so un is the periodic part of the block function. So if this is block wave function, then it goes as e to the power I k dot r vectors u and k. Okay, so these are the periodic part of the block function. These are periodic because un un r we usually write. So un r is the position, and this is the lattice vector equal to un r. That's why we call it periodic. And then I del k, or rather grad k, okay. So this is the Berry curvature, and integration of this k space integration 1 by 4 pi square Chern number omega z kx ky dkx dky. So this is Chern number, okay. And it turns out that in sorry, what was your question? Sorry.
Okay. My question was like, if I have same question like as initially asked, but what are the steps? Like, I have one material. I can, there are two ways, like one can, I experimentally, I can say it's a topological material. And another thing, like computationally, I can say it's a,
Okay, yeah.
sorry. Huh.
Yeah. Okay. So I have, let's say I have some band structure or material, and I know the wave function, energy, etc. of that material in the K space. Computationally, I'm thinking. Then I
Okay.
will calculate this Berry curvature from the wave function information that I know, block wave function information that I know, and calculate with respect to kx and ky. Okay. So this is Chern number. Now, if it turns out to be 0, then it is not a Chern insulating phase, and it is not topological in terms of Chern number at least. Okay, we still cannot say ki it is topological or not topological. So it turns out that if TRS is broken, TRS means time reversal symmetry. So time reversal symmetry broken, if TRS is broken, then we often get chart number not equal to 0. So if chart number not equal to 0, so it can become 1, 2, 3, etc. Then we can say that the system is in Chern insulator phase, or the system is topological, which is determined by the Chern number, or Chern topological index, sometimes we call it. So that is the first check, that if you calculate Berry curvature integration and then
Okay, this will be
tell me.
okay. Sorry for interrupting. This will be for like if the material which shows in churn number, then it's easy, right? So if it's
Right.
not showing churn number, because there are many other type of topological phases. So there is not common formula for this, so
No,
that we
no.
can able to
There is no
identify.
common formula. So so the first check you can do is, or if you know that the system is time reversal preserved, then you don't need to calculate even Chern number, because you know that Chern number is going to be 0. So that comes from a very easy symmetry analysis under time reversal symmetry, but this actually becomes 0 in time reversal symmetric system. Or more easily, you can think that in all non-magnetic system it should be 0. Okay. When I say time reversal symmetry broken system, it should be kept in mind that I am saying that the system intrinsically breaks time reversal symmetry or not. I'm not talking about I apply magnetic field and then say that system is time reversal symmetry broken and so on. Okay, that is not the case. System should be intrinsically breaking the time reversal symmetry. Then Chern number will not come. I mean, it will be 0 if it is not broken. If it is broken, then you will have some number 1, 2, 3, etc. Similarly,
Okay.
similarly, if the time reversal symmetry is preserved, but then system has valley, like graphene has two valley actually in its Brillouin zone. Okay, graphene structure is like this, which is a honeycomb structure, and in one unit cell there are two atoms, two inequivalent atoms, A and B, and which give rise to two valleys actually. Okay, A and B. So valley means basically there is a valley literally means that when we talk about those mountains, there is a deep and then high rise, etc. So if we
A direct cone.
right, so this is, let's say, K valley, and this is again K prime valley. Although the dispersion or the energy versus K looks like same, but then if we calculate other things like this Chern number itself, okay, in a pristine graphene system, pristine graphene system with gate voltage applied, so that inversion symmetry is broken. Okay, so these are a bit advanced concept, but all I'm trying to say is that in a material where there are this kind of low in energy and then again it goes high. So if you see the band structure of graphene, how do I show? Okay, yeah. So you guys know the concept of Brillouin zone and so on, definitely, right?
Yeah, yeah.
So this will be the Brillouin zone of graphene. Not sure how much these things are relevant, but let's say this is gamma point, center of the Brillouin zone. This is in K space, and this is again some K point, and then this is M point, and this is again another inequivalent K point, K prime. So there is a particular path. If we plot the band structure around this particular path, let's say I am doing from gamma to K, this path. So we'll have this kind of lowest energy at K, highest energy at gamma, and then M, it will look like this. I can show you the exact plots later on. And then again at gamma,
Okay.
it will be like this. Oh, sorry, again K prime. So again, it will look like this, same energy, and then it will again increase gamma. Okay, and similarly valence band will also be sort of mirror type thing. Writing is very bad. So this is again gamma, and this is again k prime. So what we have done is that we have traversed from gamma, k, m, k prime, and again gamma. So this kind of system we call valley system, because there is a high energy and then kind of valley of the system in the energy space, and then again it rises to some point, and again valley, and again energy rises. So this kind of system where the graphene in the graphene where inversion symmetry is broken but time reversal symmetry is there, the total Chern number is still be 0. Okay, so here if you calculate total Chern number of the system in the whole Brillouin zone, it will be 0. But if you only focus on the Cn for the k value, okay, we can focus on that actually. Just restrict your calculation to kx, ky around this point, okay, uh, in this formula. So this will be something, let's say +1 or let's say -1, doesn't matter. And then Cn k prime is +1. So if you add this will be 0. But then value wise Chern number is there, right? So then we call the system is not in the Chern insulating phase because the Chern number is 0, but valley Chern phase because the valley Chern number is not 0. Valley Chern number has some finite value. And in Chern insulating phase we can actually do the anomalous Hall measurement, and if the anomalous Hall effect comes finite and it is quantized at some places, we can say that the system is in Chern insulating phase, which often happens in ferromagnetic insulator cases. In the valley Chern phases, we have graphene or bilayer graphene type system which preserves time reversal symmetry, meaning intrinsic time reversal symmetry. Total Chern number is 0, so total anomalous Hall effect is 0. But then there is special kind of experiment that people now are doing, which is called non-linear anomalous Hall effect. Non-linear means non-linear in electric field, whereas our convention is J equal to sigma E, right? Whatever we understand, this is current density, this is conductivity, and electric field. Similarly, there can be expansion to this problem, or let's say denoted by chi E square. So this is non-linear Hall effect, non-linear anomalous Hall effect, which can detect this valley Chern phase. And similarly, most likely quantum spin Hall measurement or quantum spin Hall effect can say that, again, this is also for time reversal symmetric system. This is also time reversal symmetric system, and this is also time reversal symmetry broken. Okay. So you will measure nonlinear anomalous Hall effect in the system. If it is coming non-zero, then you can say that the system is in valley Chern phase. And then if the Z2 topological phase, you need to calculate the spin Hall effect of the system. I think it is clear now, right? I mean, these are quite a detailed thing in its own. Each thing are very detailed, but yeah.
So do you have some resources where one can consult, I mean, in detail on this?
There are actually a lot of details and lot of materials. Depends on how much
I
deeper you
see.
want to go. Uh, so before going to all of these things,
Okay.
you need to read Berry phase theory and all of these things. Sorry, any questions?
Okay. Thank you. So okay. So like so now how to how to get not a pro, like how to understand more about this, there are many formulas you have shared me, right? So like in a
Actually, you
high
see,
level
I think, yeah. So it's not only high level. So I'll not say high level. If you study, you will definitely understand. That's not a problem. The point is key. I'm nitpicking some information, not understanding, right? I'm nitpicking some information, some equation, and saying ki this is the case. But then if you really want to study, you have to go thoroughly over it, right? You have to start Berry phase theory, how it gives rise to Chern insulating phase, and so on and so forth. So that's the point. Now there are multiple source. I mean, I cannot say one source, but there is one paper. Again, this is the just basics. Before that, I will, for a general reader, I always advise that read Griffith's adiabatic evolution page in the Griffith quantum mechanics. Adiabatic approximation or evolution, whatever, I do not remember. Adiabatic approximation probably. So this is from Griffith. And then go to the, there is a paper by Dai Xiao et al. Dai Xiao, Qiannu and Sam Chang, probably. Dai Xiao, Sam Chang or Cheng, I don't remember. And then Qiannu. The title of the paper is Berry phase theory or something like that. Just let me search. Okay, so this paper, Berry phase effects on electronic properties. So this is a review paper. Okay, so this is Berry phase effects on electronic properties. Okay, so that's one paper, and then you'll not get Z2 and all of these details very well here, but then there are other, I mean, that paper, Berry phase effects on electronic properties, will itself lead you to many more papers relevant.
Okay. Thank you.
So yeah, so in different times this has been experimented. Anomalous Hall effect has been people have been doing from maybe last 15-20 years. Nonlinear, so detecting Valley-Chern phase via nonlinear anomalous Hall effect, it's something that has been recent as probably 2021 or 2, and this is just as a side information. Our research group was involved in this, although I'm not, but yeah, in detecting this Valley-Chern phase by nonlinear anomalous Hall effect. And then people have been doing Z2 topological phase by spin Hall effect probably from 2004 and so on, at least from a theoretical perspective. Okay, so any questions?
Sir, you have told about different phases, like churn phase, valley churn phase. Suppose if we have a material, and so from where we have to start means how we can go that way, whether the material is a churn matlab churn material churn whether it is in churn phase or churn valley phase or in Z2 phase. So
Actually,
means how,
when you do materialistic calculation, I have a material, right? I'll definitely know the material is time universal symmetric or not, right? Uh, during band structure, I do not know you guys do BFT or not, because the question seems to be coming from the material enthusiasts. But yeah, so there is something called density functional theory, first principle calculation. So when you do calculation, calculate the band structure and so on, that it definitely tells that if there in the material there is a magnetic order, it is time universal symmetry broken or not. Now, if it is time universal symmetry broken, forget about Chern number. So that part is gone. Chern number you don't need to calculate. It will be anyway V0. And then if it's time universal symmetric, I have values in the system like graphene, bilayer graphene, etc. Then there can be a possibility of having Valley-Chern phase that you can calculate. Again, the Chern number, just keep your kx ky grid around these values. That is easily doable. Okay, and then Z2 topological insulator is something you calculate spin Hall conductivity, or you calculate spin polarized bands, and then you see the possibility of having Z2 topological phase or not. And it's not guaranteed, but it can be there. So the starting point always from a theoretical perspective should be the band structure calculation, and knowing the pertaining symmetries of the Hamiltonian or the system, and then building one by one that Chern number is 0, so let's look at the Valley-Chern number, or then let's look at the Z2 or any other phase maybe.
okay, thank you, sir. It means after doing DFT and determining the electronic structure only we can proceed.
Not, yeah, I mean, see, DFT is for accurate calculation, right? But if I have, you guys already probably know that graphene have a Hamiltonian like this, H bar Vf sigma dot k, right? You know this equation?
Yes.
Okay, but this is not the band structure of graphene. I mean, it cannot be, right? It will go on increasing like this in the both direction. This is not the band
Yes.
structure of graphene. This is the band structure of graphene at a particular energy range, at a particular kxky range. So what I have, this tight binding band structure will look like this one. Again, very bad writing, but this will be the case. So if even if you have this kind of low energy Hamiltonian, what we call low energy Hamiltonian, because this is the zero line, this will be the energy equal to 0. So around this point only this is valid, this Hamiltonian is valid. So even if you know this kind of Hamiltonian, which some DFT people might have done it, and then they found that around this k point and 0 energy we have a almost like linear bands. Even if you have this kind of Hamiltonian, you are good to go. DFT, for DFT you need full, you will get full Hamiltonian and so on. Even if you don't go DFT, if you just can do tight binding, then also it is fine. Okay, DFT is for
Okay.
mostly used for unknown materials, and then I mean unknown band structure, and even in the known band structure you just modify, you add some more material in the system and so on.
Thank you, sir.
Okay, so any questions?
I mean, I don't
No,
have a
sir.
question, but just a last comment on the question you mentioned about what we expect
Yes,
from
yes,
the
yes,
sessions.
yes.
So, I mean, for example, today it was overall introduction, which
Right.
was very nice. But I mean, if I personally would like to like solve some problems, for example, or something like that, then it would be more interesting. So
Yeah, sure, sir.
that's my request from next time, if that's possible. Thanks a
Yes,
lot.
yes, yes, sure, sure. Thank you for the feedback. Yeah, anyone else? Comments? Okay, so let's end today's session.
Okay, thanks a lot for your session. It was
Thank you, sir.
Yeah,
very insightful.
thank you all, and I hope you guys will join, continue.
Yeah, sure. Next time.
Yeah, sure, sir. Thank you.
Good evening to you.
Thank you, sir. Thank you.